This is part 7 of the structures of simple solids unit, and as I mentioned in the previous part, I would introduce you to polymorphism. Polymorphism is a phenomenon that exists in crystal structures where it allows the atoms to adopt different crystal forms. Okay, so you can see on the diagram on the right hand side of the slide that this shows two different forms of mercury. One is in a non-cubic form at the top, and in the bottom one you will recognize the body-centered cubic structure for mercury. The other property of metals that we need to have a quick look at is that of alloys. What are alloys? Well, alloys are simply just mixtures of metals. So for example, you will be familiar with stainless steel. Those of you who cook with stainless steel cooking pots or any other stainless steel device, that consists of a mixture of iron, chromium, and nickel. And how do we get that? Well, we simply melt the metals together in a certain percentage, and the atoms sort of mix and meld with one another for us to get an alloy. Other examples of alloys include bronze and brass. So, you know, that you basically get my point. Okay, there are two types of alloys. The first one is a substitutional alloy, where the atomic radii of the elements are within 15% of each other. The crystal structures of the two pure metals are essentially the same, and the electropositive characters of the two components are similar. All right, so in diagram A at the top over here, you have an example of a substitutional alloy, which basically means that one or two or maybe more of the green atoms, whatever they may be, have been replaced by the red atoms. Okay, the second type of alloy that we get is called an interstitial alloy. And this one is where we have a solid solution where the additional small atoms occupy the holes within the lattice of the original metal structure. So you can see that in diagram A above, they occupy actual positions, but in diagram B, as I've indicated by the orange arrow over here, and now the little black arrow, you see that it occupies, the red atom occupies holes in between the green atoms. Okay. Now, sometimes what can happen is that all the holes can be filled and we end up with a completely new structure, and the arrangement is quite regular, as you see in part C of the diagram at the bottom of the slide here. Okay. On this section diagram here, you can see this is a typical chromium substitution in the space of iron. So in this example, in part A, this is the packing of iron. You can see it's a body-centered cubic structure. And then in diagram B, on the right-hand side here, you can see that chromium now takes one of the center positions inside the crystal structure. And then you have a more substituted example down here in C, where the chromium now starts to occupy more of the positions, and you end up with the interstitial alloy. All right, what I'm going to go through with you now is binary compounds, which are basically ionic solids, and just show you some examples of the solid state packing for some of them. Okay, so binary compounds, as you learned in first year, are compounds consisting of two elements with opposite charges. So, for example, sodium chloride. The atoms of the second element will generally tend to pack in the holes of the first element's lattice. And there are two determining factors for the formation of binary compounds, is that their relative sizes will determine in which holes the second element is going to pack. If the elements are too large, it's going to change the structure, and obviously the charges of the elements must balance. So on this slide, we have a table which shows some of the examples of binary compounds and the packing arrangements that they have. So you'll see that rock salt, or sodium chloride, packs in cubic close packing. Now remember that cubic close packing is the same as face-centered cubic. So all of the mentioned structures here are cubic close packed or face-centered cubic. Okay, so that includes sodium chloride, fluoride, which is calcium fluoride, the stuff that you would use in your toothpaste to keep your teeth nice and strong, cadmium chloride, and then something called sphalerite, which is zinc sulfide. Zinc sulfide is quite unique in that it occupies two different structures, as we're going to see shortly. Right, then at the bottom of the table, we have all the hexagonal close packed structures, which are listed there. Sorry, excuse me. And you see another example of zinc sulfide. I'm going to show it to you in a later slide, where you have wurtzite. Wurtzite is another format, another crystal structure form of zinc sulfide. Okay, so let's take a look at rock salt. Rock salt is sodium chloride, and you'll see that the sodium atoms are the smaller ones in the diagram shown, especially let's look at the center one because it's easier to see. So the little purple spheres are indicative of the sodium ions, and the green spheres are indicative of the chloride ions. And this tends to be the structure of most of the alkali halides. Okay, on this slide, what we're going to see now is what the cage structure for sodium chloride looks like. All right, so this is, you can see here in this diagram here, you're familiar with the face-centered cubic arrangement. And so we have the chloride ions as the green ones here, and sodium are the purple ones here. And you'll see that the sodium ions pack into the spaces between the chloride ions. This diagram in the middle just shows you how we would look at sodium chloride to see the alternating arrangement of the sodium ions and the chloride ions. And then, of course, this diagram on the far right-hand side is the projection view. Remember, we've done fractional coordinates and projections. This is a projection view down one of the faces where it shows the fractional coordinates of the atomic positions. Okay, so if we had to look at what it's showing you, you will see that there are some numbers in brackets, which you should know about, and the colors relate to the ions themselves. So if the designation is purple, it refers to the sodium ions. And if the designation is green, then it refers to the chloride ions. And essentially, you'll see that the chloride ion, the sodium ion here is at position 0 and position 1. Now, if this were the origin over here, this we could say is position 0, and that is position 1. Okay, and then we look now to the this one here where it says 1/2, and if we go back a little bit, you will actually see that depending on where you've chosen the origin, if you choose the origin here, for example, then this one is going to be 1/2. Okay, and the position of the chloride now is in green. Okay, and that would be 0 and 1, depending on where you are, depending on which part of the cube you start with, and so on and so forth. So you can see again here the fractional coordinates. If I'm looking, I'm going to look, let's look down this way. Okay, we look down onto that face, and we can draw the fractional coordinates for sodium chloride as I've just explained. So this is an example now of a body-centered cubic structure with cesium chloride, and you will see, you should be familiar with this one. This is what I've just given you, different representations of what the structure looks like. So these are pictures taken from both of your textbooks that I've given you. You recognize this picture from the textbook showing that the cesium atoms sit on the corners of the cube, and then the chloride ion is in the center of the cube. And then, of course, I'm looking at the fractional coordinates with the projection view, which is this diagram here. and you see you'll see that you've got the cesium atoms, which are the purple ones, with their corresponding fractional coordinate over here. And then, of course, the fractional coordinate down the face for the chloride is exactly at 1/2. Now, for this slide, we have an apparent body-centered cubic structure for ammonium chloride. So the chloride ions sit on the corners of the cube, and the nitrogen appears to sit in the center, and the hydrogen atoms are oriented towards the chloride ions, as indicated by the dotted lines in the diagram. The next example I'd like to present to you is that for zinc sulfide that has a sphalerite structure. It has expanded cubic close packing or face-centered cubic. And in this diagram, part A here, you will see the face-centered cubic for the sulfides. The sulfides are represented in green, and the zinc ions are represented in purple. If you follow the pattern, you will see that the sulfides sit in face-centered cubic positions, and the zinc ions occupy tetrahedral holes in the face-centered cubic structure. On the far right-hand side here is the fractional coordinates for the atoms viewed down one of the plane projections. And I'm going to leave you as an exercise to figure out what each of these coordinates are. So you will see that this refers to the sulfides, okay, and then the purple ones are indicated. You need to figure them out for yourself, and this one refers to the sulfide as well. Try to do this example on your own. It's not difficult. You should be able to see from the actual structure that, for example, this one here is 1/4 of the way up if you worked out the entire distance. You should be fine working that example out, and contact me via the normal channels should you want to get me to explain it to you so that your understanding is clear. All right, the other form of zinc sulfide is the wurtzite structure, which is expanded hexagonal close packing. Again, on diagram A over here, it shows you what the packing looks like. Okay, again, representing the zinc ions in the color purple, and the sulfide ions are in green. And on the far right-hand side over here is the projection view showing the fractional coordinates. Okay, I'm not going to expect you to figure this one out for yourself because this particular structure is quite tricky, but just understand that the position of the sulfide is in 0 and 1. So if we chose this one here, for example, 0 and 1, and then the zinc happens to be 3/8 away. So if we measured this distance here, it would be roughly 3/8 from the origin. And similarly for the this sulfide over here, it ends up being 1/2, okay, from the a-axis, and then this one here will end up being in position 7/8. I don't expect you to know that, but that's how it's calculated. All right, the next example is calcium fluoride, otherwise known as fluorite. The calcium is again packed cubic close packed or face-centered cubic. It's surrounded by 8 fluoride ions occupying all the tetrahedral holes. Okay, so in the diagram on the left-hand side over here, the calciums are represented in purple and the fluorides are in green. You can see that the calciums occupied face-centered cubic positions, and then the 8 fluoride ions occupy the tetrahedral holes because there's tetrahedral geometry around the fluorides, and there are subsequently 8. You can count 8 atoms in the structure that I've indicated. Okay, next to it in diagram B, this one here, is again a projection view showing you the positions of the atoms as well as their fractional coordinates. And this one I think is not too difficult to work out. You can, they give you positions of the fluoride ions, so that'll be at 1/4 and 3/4. They give you positions of the calcium ions at 0 and 1, depending on where you choose the origin. So if you choose the origin over here, you can see that that's a 0 and that's a 1. And then this is 1/4, this is 3/4, and so on and so forth. And then this one will be at 1/2. Okay, so this one I would expect you to be able to reproduce. So if I give you a diagram like this diagram here in an assessment, then I would expect you to be able to possibly even draw the 3-dimensional structure of the particular material. Okay, this example is for titanium dioxide, the rutile structure. It's a distorted TiO6 octahedra. Okay, so in this instance, I'm going to use this top diagram to give you some idea of what you can see. So the center atom is the titanium and the red atom is the oxygen. In the bottom diagram here, it's just indicated differently, where the titanium is given in purple and the oxygens are given in green, and the fractional coordinates down one of the projection axes is given to you here. It's again also not too difficult to work those ones out. The purple indication shows you where the titanium atoms are, and the green shows you where the oxygen atoms are. You can it's a complicated structure, yes, but it's still it's one of the hexagonal close packed structures that you would remember that we've spoken about already.